Hello, we're going to talk about the graphs of rational functions and how to get them, how to talk about them. So let's talk about how you might graph them. Let's suppose that I have a reciprocal function, a pretty simple reciprocal function, like y equals, I don't know, I'm just going to make one up here, 1 over x minus 4 plus 2, let's say. So one of the things we got to remember, we got to keep in mind, is what the parent function looks like, the parent function being the simplest version of this family of functions. And the parent function looks like that. It has an asymptote there, it has an asymptote there, and the graph runs along the asymptotes in this way. Remember, it just keeps going closer and closer to the asymptotes, but never touches them, never crosses them. That's what an asymptote is. It does have this magical moment between there and there where it sort of magically jumps over at an infinity point, either negative or positive, depending on which side you're looking at and how you're looking at it running. Okay? So that's what the parent looks like. And then we want to note, most importantly, the shifting. So this here, this x minus 4, the minus 4 is grouped in with the x because it's in the denominator with the x. So let's talk about the shifts. And there's one in the x direction. Shifting in the x direction happens when it's grouped in with x and happens the opposite of what you see. So the shift in the x direction is positive 4 because we see a minus 4 or a negative 4 there. The shift away from happens in the y direction because it's not grouped with x, and happens as you see it. So the shift in the y direction is plus 2. Shifting happens in equations when you have pluses and minuses, okay? That is when you have addition and subtraction. And the shifting for these reciprocal functions, the easiest thing to tell that it moves is the asymptotes, okay? So like the vertical asymptote, that one, is going to shift in the x direction because shifting that one in the y direction doesn't matter because it goes up and down forever. So movement on it in the y direction doesn't make a difference to it. But movement in the x direction makes a lot of difference to it. So it's going to move positive 4 in the x direction. So there's my new vertical asymptote. And then the y direction one moves the vertical asymptote because the only direction that it matters for the horizontal asymptote is in the y direction. So positive 2. And so that one has moved like that, and there's my new asymptote. And other than that, because there's no multiplication going on here, no multiplication going on here, no negatives, no other weird stuff going on, that's the only thing that happens. And other than moving that, the graph itself looks the same. So it looks just like it did otherwise. Now, if I were to put a negative out there, and I won't keep it there, but if I were to put a negative out there, what would happen is it would flip in the y direction because that negative is out here away from the x. And so up would become down and down would become up, and that's what negatives do. If I were to get multiplication going on, if I were to multiply this by something, then I would get stretching or shrinking, depending on how that works. The shifting is the easiest thing to see. The next easiest thing to see is the flipping. The stretching and shrinking is really hard to determine because your scale can change. And if your scale changes, it just doesn't matter that you had stretching or shrinking. If you change your scale as much as you did the stretching or shrinking, then you can't even tell that you did it. So stretching and shrinking, if you really need to go that far, then you need to build a table for it or use technology to graph it. Okay? So that was sort of the really easy one. Let's talk about another one. Let's determine the slant asymptote for the following function. And I have to talk about how you know that this has a slant asymptote, but let me make one up here. Let's say we got 2x squared plus 5x minus, I don't know, 7 over x plus 3, let's say. So how do I know that this has a slant asymptote at all? And the answer is the degree of the numerator is 1 more exactly than the degree of the denominator. And that's how I know I have a slant asymptote for this. And the way you figure out what the slant asymptote is you have to do long division. Okay? So what you do is you say, okay, I'm going to do the top divided by the bottom, just doing the division that I'm being told to do here, and just do that division. So I need to multiply by this to make this, and I'd have to do 2x times x to get 2x squared, so I'm going to put a 2x up here, and then 2x times x is 2x squared plus 2x times 3, so that I'm distributing that 2x, is 6x. And then you have to subtract these, and the way you do that is you change the signs on both of them so that you are subtracting. And those two cancel. Those two better cancel. You design them so that they will cancel. And then 5x plus negative 6x is negative 1x, or just negative x. Bring down the minus 7, put a plus up here, and start the game over again. So now I got to multiply by this to make that, and negative 1 times x is negative x, so I'll put a negative 1 up here, and that'll be negative 1 times x is negative x, and negative 1 times 3 is negative 3. Change the sign so that I am subtracting. Those two cancel, they better cancel, that's how you designed it. And then negative 7 plus 3 is negative 4. And so your remainder, the way you write it, is plus negative 4 over x plus 3. And then this you take as x goes to infinity, which means that this part goes to 0. And the equation for the slant asymptote is y equals, and then you just take this essentially without the remainder, 2x plus negative 1. So how would that help you in graphing this? Well, it gives you two asymptotes to deal with. First of all, you have a vertical asymptote, which you can always tell by what would make the denominator 0. So if I was graphing this, there'd be a vertical asymptote at negative 3, because if I put negative 3 in for that x, negative 3 plus 3 is 0. So there's a vertical asymptote at negative 3. And then there's a slant asymptote, and that's the equation for it right there. So if I think of a little table for this, an xy table, if I were to put in 0, I'd get negative 1. If I were to put in, let's say, 1, I'd get 1. So 0, negative 1, and 1, 1 is the equation, is the model for my slant asymptote. And then these functions wind up looking like, a lot of times, like that and like that. I didn't leave myself a lot of room at the bottom there, but that's what they wind up looking like. So that's for functions with a slant asymptote. Let's talk about how to graph ones where we get something a little more complicated or something a little bit weirder. Let's say we wanted to graph like y equals, I don't know, x minus 3 over, I don't know, I'm just going to make something up here, x cubed minus 2x squared plus 3x minus 4. So what I'm going to do with this, and I actually made this pretty tough on myself. You know what? I made this too tough on myself. Let me do something that I can handle a little bit easier. Okay. Over x squared plus 5x plus 6. Okay. That'll be a whole lot easier to do. Okay. So what I'm going to do is I'm going to figure out what the asymptotes are first, and notice the degree of the numerator of the top is 1, the degree of the denominator is 2. In order for there to be a slant asymptote, the degree of the numerator of the top must be 1 more than the degree of the denominator, the bottom. That is not the case here. The bottom is 1 more, and that doesn't matter. Okay? So I'm going to have a situation of horizontal and vertical asymptotes here. So here's how I'm going to figure out what those are. I am going to start by getting the vertical asymptotes. And the way I'm going to do that is I'm going to set the bottom equal to 0, and I'm going to solve it. And the reason I wrote this one is because it factors real nice into x plus 2 and x plus 3. And then that means that either x plus 2 equals 0 or x plus 3 equals 0. And then you subtract 2, and you get x equals negative 2, or you subtract 3, and you get x equals negative 3. So that's where my vertical asymptotes are. So if I'm sort of starting to graph this, I've got one vertical asymptote at x equals -3. I've got one vertical asymptote at x equals -2. And then I got to figure out what in the world is going on. But before that, I got to figure out my horizontal asymptotes. To figure out the horizontal asymptotes, you divide everything by the highest power term and look at it again. So the highest power term is x squared, so it'd be x over x squared minus 3 over x squared over x squared over x squared plus 5x over x squared plus 6 over x squared. And then what you do is you say, okay, what happens as x goes to infinity? And for a lot of these, what happens is they go to 0. Okay, that goes to 0, that goes to 0. This is 1, so that's going to stay a 1. This goes to 0, this goes to 0. And so I get 0 over 1, which is 0. And that tells me where my horizontal asymptote is. My horizontal asymptote is at y equals 0. Okay, so that means my horizontal asymptote is right there. Then these don't fit any certain pattern, and that is the real crux of this. So what you have to do is you have to build a table, and the values that you have to pick, let's say I was building a table here, the values that I would have to pick would be somewhere to the left and right of each asymptote. So I might pick -5, -4, -3 doesn't help me, -2 doesn't help me, so it better be like -2.5. And then maybe -1 and 0. And that should tell me something. It would be nice to pick more than just -2.5. In fact, I should probably have picked -2 3/4, -2.5, and -2 1/4, and that would have given me an even better idea. But you plug these in and you start to see what goes on, and where you plug them in is into the original equation. Okay, so like if I put in -5, I get -8 over what, 25 minus 25. Well, that's convenient, so that's 0 plus 6. So -8 over 6 is a little less than -1. So if I'm looking at -5, it's somewhere between -1 and -2, kind of like that. If I plug in -4, we're talking -7. And then we're talking, what, 16 minus 20 is -4. -4 plus 6 is 2. So -7 over 2, which is -3.5. So -3.5 is somewhere like that. So this one would follow the asymptotes kind of like that. And then you got to figure out these -2 and 3/4 and -2.5, and so let's see what would happen say a little less than -2 would be -2, and -3 would be like -5.5. And then let's see here. -2.5 squared is -5.5 squared, which is 25/4, which is just about 6. And then 5 times 5 halves is 25 halves, which is 12.5. So that's 6 minus 12.5, something like that. So around -6.5. So around 1/2 on the bottom. And on the top, -5.5. So -5.5 divided by about 1/2 is like multiplying by 2. So what is that? 11/2 is 5.5. So -11. So that's -11. So what that tells me is that what happens here, so it's way down here somewhere, and what that tells me is that this probably does something like this, and it just keeps following those asymptotes. Okay, and then if I do -1, that should be a much simpler thing. -1 minus 3 is -4. -1 squared is 1. So 1 minus 5 is -4. -4 plus 6 is 2. So -4/2 is -2. So that's kind of like that. And then 0 should be a lot easier. -3/6, which is -1/2. So there, and then this one does that same thing as on the other side. And so it starts to look like that. But I want you guys to be really careful because there is no telling how these turn out. They all look weird. And they all do weird stuff, and they can have all these weird asymptotes and weird turns and curves, and sometimes they don't seem to follow the rules and all sorts of stuff. What I would say is at least double check them with technology like Desmos.com. Okay? So that's those. The next helpful thing then is what if I gave you a graph? What if I told you that here's a graph. Let me create one. And what if I told you that the parent was 1/x, and I want you to give me this function? Well, here's what you could do. You could say, okay, it looks like there's a horizontal asymptote there. It looks like there's a vertical asymptote there. And what I would do is I would say, let's assume there's only shifting. Okay, because if they're stretching, again, let's say the only possibilities are shifting and flipping. Okay, so this one, remember the parent function has these asymptotes and looks like that and that, sort of. So this looks like that. It hasn't flipped, obviously, but it certainly has moved. So let's say it's moved like that. Okay? So let's write down the shifts, just like we did when we had the equation. In the x direction, we're talking a shift of -2. In the y direction, we're talking a shift of -1. And so if this is the parent, the function that I've currently got there, let's say it's f of x, is, let's keep it at 1 over, and grouped with the x, the -2 is the opposite of what you would see, so I would see a +2, and the y direction is not grouped with x, and that happens exactly as I would expect, so that would be my equation. Okay? Let me double check and make sure there isn't anything else that I really need to talk about. I don't think so. I think that's it. So thank you again for watching. I hope this has helped.